Hello and welcome to The Sleepy Scholar. This evening we are going to explore one of the most profound and alluring questions in the scientific world. Is it possible that life on our planet did not begin here at all? Could the initial catalyst for biology have been delivered drifting across the immense quiet voids of the cosmos? This concept is known as the panspermia hypothesis, and it implies that the narrative of life is far grander, more ancient, and more enigmatic than our conventional understanding. Over the course of our journey tonight, we will investigate how biology might migrate from one world to the next, what manner of cosmic transport could provide passage, and what modern experiments have revealed about life's capacity to survive in space. We will examine meteorites that have landed on Earth, carrying within them the complex organic molecules that form the basis of our own bodies, and ask if they are telling us something about our ultimate lineage. And we will ponder what it would signify if the seeds of biology are not unique to our world, but are scattered throughout our solar system, and perhaps across the entire galaxy. If you find solace in these quiet explorations of the cosmos, you can support the channel by liking this video, subscribing, or simply leaving a peaceful thought in the comments below. It assists other curious minds in discovering this space. But for this moment, find your comfort, quiet your breath, and allow your mind to drift. Let us commence. The term panspermia is derived from Greek roots, pan meaning all, and sperma, meaning seed. The concept itself has ancient origins. Thinkers in antiquity, such as the philosopher Anaxagoras, wondered if the seeds of life might be adrift in the cosmos. But the modern scientific articulation of panspermia truly begins with the Swedish scientist Svante Arrhenius in the early 20th century. Arrhenius put forth a concept he named radiopanspermia. This was the hypothesis that microscopic spores, so infinitesimal and light, could be propelled through the vacuum of space by the faint, persistent pressure of starlight. He theorized that resilient bacterial seeds could effectively ride these beams of radiation, journeying between star systems and, perhaps, eventually finding a fertile new planet to colonize. This idea was both captivating and unsettling. It was poetic, yet it also suggested that our Earth was not the self-contained cradle of life we had always assumed it to be. Throughout the 20th century, scientists re-examined this theory in new ways. Francis Crick, who famously co-discovered the structure of DNA, even postulated directed panspermia, the speculative possibility that life was intentionally seeded on Earth by an advanced extraterrestrial intelligence. Presently, panspermia exists on the periphery of mainstream scientific consensus, but it has never fully vanished. Instead, it has adapted, shifting from broad philosophical speculation to a collection of testable, albeit incredibly challenging, hypotheses. Modern space exploration, sample return missions, and laboratory simulations continually add new, intriguing pieces to this puzzle, enough to ensure the idea is never entirely dismissed. Scientists generally categorize panspermia into three distinct flavors. The first, lithopanspermia, is the most physically plausible. In this model, rocks are blasted from a planet's surface by a major asteroid impact, carrying microorganisms shielded deep within the stone. Protected by this rocky matrix, these tiny pioneers might withstand a long, dormant journey through space before eventually crashing onto another world. Studies of the exchange of meteorites between Earth and Mars have proven that this transportation mechanism is, in fact, real. The second, radiopanspermia, is Arrhenius's original concept. In this version, spores or cells small enough to be moved by radiation pressure are swept across interstellar distances. The great difficulty here is the severe, unfiltered exposure. Lacking a shield, cosmic rays and hard ultraviolet radiation would likely annihilate delicate molecules in a relatively short period. Still, experiments continue to probe the limits of life's endurance in the open vacuum. The third, directed panspermia, remains the most controversial. It posits that life on Earth was not an accident, but an intentional act of seeding by an intelligent species. Francis Crick and Leslie Orgel introduced this idea in the 1970s, not necessarily because they thought it was probable, but to stimulate new thinking about the ultimate origins of life. Some contemporary researchers have mused along similar lines, though most regard it as a subject for science fiction rather than a practical scientific hypothesis. Together, these three versions create a spectrum of thought, from the plausible to the possible to the truly provocative. And they remind us that panspermia is not a single theory, but rather a family of related concepts, each one asking the same audacious question: what if life is far more mobile than we ever imagined? But why contemplate panspermia in the first place? Is it not sufficient to study the origins of chemistry here on Earth? The importance lies in the profound shift in perspective. If panspermia played a role, it redefines our place in the universe. If life began on another world and was transported here, then our lineage is not strictly terrestrial. Our ancestral tree would have roots extending beyond our own planet, perhaps to an ancient, wetter Mars, an icy moon, or even a different star system entirely. This would imply that the story of biology is older than Earth itself, and that life is not a singular local event, but a cosmic traveler. Another factor is probability. If life can move between worlds, its emergence might not be the improbable miracle many believe it to be. Instead of being an isolated phenomenon, life could seed many different environments across the galaxy. Each new world would not need to independently invent biology from inert chemistry. It could simply inherit a biological starter kit. That concept makes the universe feel more connected, more alive, and more filled with potential. Finally, panspermia compels us to reconsider the boundary between here and out there. Earth is not an isolated system, it is in constant exchange with the solar system. Meteorites arrive every day. Cosmic dust rains down constantly. The universe is permeable, and if complex molecules or even microbes can withstand the journey, then the barrier between worlds may be far thinner than we perceive. Among scientists, panspermia occupies a very delicate and specific position. It is not the reigning theory for life's origin on Earth, yet it is not rejected as mere fantasy. It is treated as a plausible hypothesis that merits rigorous testing. Most mainstream researchers concur that lithopanspermia, the exchange of rock, is physically feasible. We have tangible evidence that this happens, and simulations show that microbes shielded by rock could, in principle, survive the transfer. What we do not know is whether it actually happened. Radiopanspermia, while imaginative, faces greater skepticism. The lethal exposure to radiation and the immense timescales involved seem insurmountable for fragile biology. Experiments in low Earth orbit have demonstrated survival for months or years, but not the millions of years required for interstellar travel. Directed panspermia is held in the least regard by the scientific community. It veers into speculation about alien motivations, and without any evidence, most scientists leave it to the realm of philosophy. Where caution is essential is in addressing fringe assertions. Sensational announcements of alien microbes in meteorites or mysterious red rains carrying supposed extraterrestrial cells have been made. These claims have, invariably, failed to withstand rigorous scientific scrutiny, reminding us all that extraordinary claims require extraordinary evidence. A common misunderstanding is that panspermia seeks to supplant the theory of abiogenesis, the natural, spontaneous origin of life from non-living chemistry. In truth, most scientists who explore panspermia view it as a potential complement to abiogenesis, not a replacement. Abiogenesis remains the most widely accepted and studied explanation for life's beginnings. Experiments continue to explore how simple molecules could assemble into complex chains and how those chains could become self-replicating. Panspermia does not eliminate this fundamental question, it simply relocates it. If life was delivered to Earth from space, it still had to originate somewhere else at some earlier time. Think of it as tracing a river to its source. Abiogenesis describes the spring, the location where chemistry first crossed the threshold into biology. Panspermia simply asks whether that spring bubbled up here on Earth or on another world first. It doesn't remove the need for the spring, it just moves the address. In a way, panspermia could even make abiogenesis more probable. If many worlds in the early solar system, Earth, Mars, icy moons, were all running this chemical experiment simultaneously, the odds of success somewhere would rise. Life might have emerged in several places, but only one of those lineages was successful enough to thrive and spread. Earth, in this view, is not a singular, isolated miracle, but perhaps just the most successful part of a wider, regional network of biological attempts. This synthesis keeps both crucial questions active: how does life begin, and how far can it travel? Now that we have defined panspermia and its place in scientific thought, we can turn to the evidence. This is where the concept transitions from philosophy to testable science. The first line of supporting evidence comes from physics. We have confirmed that planetary impacts are sufficiently violent to eject rock into space at escape velocities. We know for a fact that meteorites from Mars have been discovered on Earth, bearing the chemical traces of the Martian environment. If the transport vehicle exists, the next question is clear. The second line of evidence is biological. We have discovered extremophiles, organisms like bacterial spores, lichens, and tardigrades that show incredible resilience. They can survive profound cold, vacuum, and high doses of radiation. Exposure experiments conducted on the exterior of the International Space Station have confirmed survival for years. These are powerful hints that biology is far tougher than we once assumed. The third line comes from astrochemistry. Meteorites have been analysed and found to contain amino acids, sugars, and nucleobases, the literal building blocks of life. Recently, sample return missions from asteroids like Ryugu and Bennu have definitively confirmed the presence of these organic molecules, including uracil, one of the key letters in RNA. While these are not signs of life itself, they prove that the cosmos is rich in these ingredients for life. And then there are the open questions. Could microbes truly withstand the entire journey, the violent ejection, the long transit, and the fiery atmospheric entry? How long can life remain viable in space before radiation inevitably degrades its genetic code? And if life did arrive here from space, why have we not yet found any definitive evidence of similar life elsewhere? In the sections that follow, we will trace these lines of inquiry. We will examine the mechanics of the journey, the endurance of life, the cosmic couriers, and the experiments that might one day provide an answer. Step by step, we will weigh the probabilities until we can see just how close or how far panspermia may be from the truth. When a planet is struck by a large asteroid or comet, the energy unleashed is almost unimaginable. Bedrock shatters, shock waves propagate through the crust, and a plume of debris is ejected skyward at immense speeds. Most of this material will fall back to the surface, but a small fraction of it will achieve escape velocity. This is where the concept of spallation becomes critical. In the upper layers of rock near the impact, but not at the center, fragments can be blasted free without being subjected to sterilizing heat. If the physics are just right, a piece of rock can be accelerated outward, its interior remaining cool, shielding anything trapped inside. For biology, this narrow survivability windows everything. Too close to the impact, and the rock is vaporized. Too deep, and it never leaves the planet. But in between, there is a path where microbes could be launched into space. We know this ejection process happens because we have collected and catalogued meteorites on Earth that we know came from Mars. These are tangible proof. If the rocks can make the journey, the next question is, can life make it with them? Once launched, these fragments enter an environment of profound hostility. The vacuum pulls away all air and moisture. Temperatures plunge into a deep freeze. Relentless radiation from the sun and from deep space cosmic rays bombards every surface. And then there is the variable of time. A journey between planets can take thousands or even millions of years. For any unprotected organism, this is a death sentence. Ultraviolet light will sterilize a surface in seconds. Cosmic rays will slowly pulverize complex molecules like DNA. However, inside a sufficient shield of rock, the conditions are moderated. A few centimeters of stone can dramatically reduce the radiation dose. Spores, in a state of desiccated dormancy, might last for astonishingly long periods if they remain shielded. Experiments where spores were exposed on the outside of the International Space Station showed they could survive for years. Shielded in the deep interior of a meteorite, it's plausible that survival times could extend significantly. The transit phase is incredibly harsh, but it is not an automatic sterilization. Biology's most resilient forms could, in theory, drift in a state of suspended animation, waiting. A fragment's journey is only complete when it encounters another planet. But this final stage, atmospheric entry, is perhaps the most perilous. Moving at tens of kilometers per second, the rock compresses the air in front of it, generating a superheated plasma fireball. The entire outer surface of the meteorite melts and vaporizes. The shock of deceleration is immense, and yet once again the shielding of the rock is key. A large meteorite acts as its own ablative heat shield. Its interior can remain cold or even frozen, even as the exterior is incandescent. If microbes were buried deep inside, they could be protected from the heat. Laboratory simulations have verified this. In one study, spores were sealed inside artificial meteorites and survived re-entry when flown on space capsules. Landing is the final filter. A high-speed impact can sterilize the cargo, but smaller meteorites, slowed by the atmosphere, can fall at terminal velocity, landing relatively gently. The probability of all these steps aligning is low, but over geological time, even low probability events happen. Arrival is an extreme filter, but not an impassable one. Space is not a random void. The orbits, resonances, and gravitational pulls of planets create pathways of gravitational influence, which scientists refer to as dynamical highways. When debris is ejected from a planet like Mars, its trajectory is not random. It is often guided by these highways, which can steer it into orbits that eventually cross paths with Earth. Computer simulations show that these transfers between Earth and Mars can, in rare cases, be surprisingly fast. While the average journey takes millions of years, a small fraction of ejecta can arrive in just a few decades. These fast tracks are critical for the panspermia hypothesis, as they shorten the survival window needed for a microbe to have a chance. Jupiter's immense gravity also acts as a great sculptor of these paths, sometimes flinging rocks out of the solar system and other times nudging them inward. The solar system is a dynamic, interconnected system, and its motions provide opportunities for matter and perhaps life to move between worlds. In 2017, astronomers detected something new, a strange, cigar-shaped object tumbling through our solar system, moving too fast to have originated here. It was named Oumuamua, a Hawaiian name meaning a messenger from afar. Just 2 years later, another visitor, comet Borisov, was spotted. It streamed gas and dust, but its trajectory confirmed it was an interstellar traveler. These discoveries fundamentally changed our view of panspermia. Interstellar objects are not just theoretical, they are common, passing through our solar system with regularity. If these objects carry ice, organics, or even dormant life, they could act as couriers, connecting star systems across the galaxy. The exact numbers are unknown, but estimates suggest trillions of these. Rogue objects are adrift in the galaxy. If even a tiny portion of them harbor the seeds of biology, then the exchange of life between stars, while improbable for any single rock, might be a real factor in the galactic spread of life over billions of years. The most poetic version of panspermia is also the most physically delicate, radiopanspermia. In this scenario, tiny spores are propelled by the gentle, constant pressure of starlight itself, pushing them out of their home star system and into the interstellar void. On paper, the physics is sound. Radiation does exert a tiny push, and we know dust grains are moved by it. But biological matter is not theoretical. A spore, exposed directly to the unfiltered light of a star, would face a lethal, sterilizing bath of ultraviolet radiation, which would shatter its DNA in mere hours. Cosmic rays add another layer of destruction over the long journey. Even if a spore could survive the initial radiation, the durations involved, millions of years to cross the gulf to another star, make survival highly improbable. Laboratory tests confirm this. When microbes are exposed to the vacuum of space without shielding, most perish very quickly. A few hyper-resilient organisms can last for months or years, but this is nowhere near the timescale needed for an interstellar voyage. Shielding inside dust or ice would help, but at that point, the mechanism is no longer radiopanspermia, but rather a form of lithopanspermia. This does not make the concept useless. It remains a beautiful thought experiment. It reminds us that the universe is in motion and that light itself can move matter. But as a viable theory for the origin of life on Earth, the consensus is that radiopanspermia, while evocative, is unlikely. Its legacy persists as a testament to the imagination required to even ask these cosmic questions. Life possesses an extraordinary adaptation for survival, dormancy. When the environment becomes hostile, certain organisms do not fight. They simply pause. Bacterial spores are the quintessential example. Encased in a durable protein shell with their DNA tightly coiled and their water content almost zero, they can wait. Heat, cold, desiccation, and radiation are all less damaging when the organism's metabolism is effectively frozen. Viable spores have been recovered from ancient salt crystals after millions of years of geological slumber and were successfully revived. Seeds represent a parallel evolutionary strategy. Though far more complex, plants package their embryos in armor designed to survive winters, droughts, or even fire. A lotus seed, recovered from a dry lake bed, was successfully germinated after remaining dormant for over 1,000 years. These are terrestrial adaptations, not ones for space. But they demonstrate biology's profound, hidden resilience. If an organism can wait for millennia inside a salt crystal, it's plausible to imagine it waiting inside a rock during a long cosmic journey. Dormancy does not make survival certain, but it dramatically extends the boundaries of possibility. Speculation is one thing, but experimentation is another. To truly test the limits of life's survival, researchers have sent organisms to the International Space Station and attached them to the outside. These exposés missions have placed microbes, lichens, algae, and even simple animals in the raw, unfiltered environment of space for months or years. The results are both sobering and astonishing. Unshielded organisms die quickly from the hard ultraviolet radiation. However, when shaded or tucked into protective layers, some survived for years. Bacterial spores, sealed within simulated rock crevices, were found to be viable after 6 years in orbit. Even lichens, which are complex symbiotic organisms, resumed normal metabolic activity after nearly 2 years of full exposure. The Japanese Tanpopos experiment studied how microbes might travel on dust. Samples were mounted on the station's exterior for up to 3 years. Upon retrieval, some were still alive. This proved that microbial passengers could, in principle, survive long enough for an interplanetary transfer if shielded by even a thin layer of material. The lesson from these trials is clear: unshielded life is sterilized quickly. But shielded life, hidden in cracks or dust, can persist for years, a timescale perfectly compatible with the fast-track's journeys between Earth and Mars. No experiment has proven survival over millions of years. But the fact that survival is measurable at all elevates panspermia from pure speculation to a testable, scientific hypothesis. It shows us that biology, while fragile, has a toughness we are only beginning to appreciate. For sheer multifaceted endurance, few creatures can rival the tardigrade. These are tiny, 8-legged water bears with a slow, endearing gait. When conditions become unsurvivable, tardigrades can enter a state of suspended animation known as a toon, expelling their water and halting their metabolism. In 2007, this resilience was put to the ultimate test. They were sent into open space. Exposed for 10 days to the vacuum and unfiltered radiation of the cosmos, many died. But a portion of them survived and were later rehydrated and successfully reproduced back on Earth. This was the first proof that a complex, multicellular animal, not just a microbe, could survive direct exposure to space, at least for a short time. Tardigrades themselves are not likely cosmic travelers. Their survival times are too short for interplanetary journeys. But they serve as an important benchmark. If a complex animal can survive for days, it is not unreasonable to think that simpler, hardier spores might survive for vastly longer periods when protected. Tardigrades are a reminder that life doesn't always break under pressure. Sometimes it just waits. Ejection from a planet is a violent, energetic event. A rock blasted into space experiences immense acceleration and shock. For panspermia to be viable, life must survive not just space, but the launch and landing. To test this, scientists have simulated these shocks. They have fired projectiles containing microbial spores into rock samples at high velocity. A fraction of the spores survived these simulated impacts, enduring accelerations tens of thousands of times Earth's gravity. The outer layers were sterilized, but deep in the pores, life held on. Atmospheric entry is the other great filter. Temperatures soar as the meteorite burns. But, again, experiments embedding spores in heat-shielding material have shown they can survive. In one test, samples returned from orbit on a capsule endured the fiery descent. In others, spores in artificial meteorites survived simulated re-entry in furnaces. These results point to a narrow, but not zero, window of survivability. Not every microbe would survive, not even most. But over billions of years, with countless impacts, even a rare success becomes significant. Biology does not require certainty, only a non-zero possibility repeated over geological time. Shock and heat are filters, but they do not reduce the odds to zero. The most relentless threat in transit is radiation. Cosmic rays and solar particles slice through molecules, breaking DNA strands. For life in space, the threat is not instant death, but the cumulative damage over time. Over thousands of years, mutations and breaks accumulate until the genetic code is unreadable. Yet, biology is not without its defenses. Spores pack their DNA with protective proteins. Some microbes, famously Deinococcus radiodurans, possess remarkable DNA repair mechanisms. This Conan the bacterium can have its genome completely shattered by radiation and then meticulously stitch it back together. The critical variable is time. If a transfer between worlds takes decades, survival is plausible. If it takes millions of years, the mutational load becomes overwhelming, even for the hardiest repair crews. The journey is therefore a race between the speed of the transit and the pace of genetic decay. Survival depends on the biological time budget outlasting the cosmic journey. As scientists have grappled with the resilience of life, they've had to confront a practical and sobering implication. If life can survive space travel, then our own probes could become unintentional delivery vehicles. A lander that is not perfectly sterilized could introduce Earth microbes to Mars or the oceans of Europa. This is forward contamination. This concern has led to rigorous planetary protection protocols. Spacecraft destined for sensitive worlds are assembled in sterile, clean rooms, baked in ovens, and irradiated to minimize any microbial stowaways. The protocols are not perfect, but they reflect a serious commitment to not contaminating an environment before we can study it. This protection is reciprocal. If we ever bring samples back from Mars, they must be strictly quarantined to prevent back contamination, the introduction of alien microbes to Earth. Whether or not panspermia is real, the possibility of it forces us to be more careful explorers. It is a reminder that exploration must be balanced with profound caution. Each day our planet is showered with material from space. Most of it is microscopic dust, burning up as shooting stars. But larger pieces, meteorites, survive the fall and reach the ground. In total, tens of thousands of tons of this extraterrestrial matter arrive annually. These meteorites are diverse. Some are iron, from the cores of shattered asteroids. Others are stony. A rare and precious subset, the carbonaceous chondrites, are dark, primitive, and rich in organic compounds. These are prized because they are time capsules containing chemistry that predates our solar system. What makes meteorites vital for panspermia is their function as heat shields. As they blaze through the atmosphere, their exteriors vaporize, but their interiors can remain cold. Any complex chemistry, or in principle life, buried deep inside would be protected from the fiery plunge. Meteorites are not mere rocks, they are natural transport capsules, messengers from elsewhere in the solar system. In 1969, a brilliant fireball exploded over Murchison, Australia. Locals collected the dark, blackened fragments. Scientists quickly realized they had something extraordinary, a carbonaceous chondrite, recovered quickly, minimizing terrestrial contamination. The Murchison meteorite became one of the most important rocks ever studied. When analyzed, it was found to contain something astonishing, over 70 distinct amino acids. Some of these were the same 20 amino acids that all life on Earth uses to build proteins. Many others were entirely alien to earthly biology. This proved, unequivocally, that the complex organic synthesis of life's building blocks occurs naturally in space, without the need for biology. Even more intriguing was its chirality. Amino acids exist in two mirror-image hands, left and right. Terrestrial life is exclusively left-handed. Why this is a total mystery. In the Murchison meteorite, scientists found a small but definite excess of the left-handed versions. This hinted that cosmic forces, perhaps polarized light in interstellar clouds, might bias chemistry in the same direction that life eventually chose. The Murchison meteorite showed that life's chemical toolkit could have been delivered, pre-assembled, and perhaps even pre-biased from space. Whether or not life hitched a ride, the chemistry certainly did. Murchison was just the start. Other meteorites have revealed their own chemical treasures. In 2000, a fireball detonated over Tagish Lake in Canada. Fragments were collected from the pristine ice, ensuring minimal contamination. Analysis showed Tagish Lake was also rich in organics, but its chemical signature was different from Murchison's, showing that different asteroids create different organic inventories. The Uracil meteorite, which fell in France in 1864, was another fragile carbonaceous chondrite, while early, sensational reports of microfossils within it were later debunked as contamination. Its rich, undeniable chemistry confirmed the pattern. Uracil, Murchison, and Tagish Lake are a chorus, telling us that organic molecules are not rare flukes. They are a common theme in the cosmos. Each one is a glimpse into the diverse prebiotic chemistry that was available to the early Earth. For decades, scientists had to study meteorites after they had been contaminated by Earth's environment. Earth's air, water, and microbes quickly invade these fragile rocks, making it difficult to know what is truly alien. This is why sample return missions represent a monumental leap in understanding. They collect pristine material and bring it back in a sealed container. Japan's Hayabusa 2 mission visited the asteroid Ryugu. It collected surface material and delivered it safely to Earth. When scientists opened the capsule, they found dark grains rich in carbon. Within them, they found amino acids and, critically, uracil, one of the 4 essential bases of RNA. This was the first time a fundamental ingredient of our genetic code was found, unambiguously, on an asteroid. Ryugu also contained niacin, vitamin B3, which is vital for metabolism. These molecules showed that asteroids are reservoirs of biological precursors. NASA's OSIRIS REx mission to asteroid Bennu returned its sample in 2023. Early analysis confirmed abundant organics and, strikingly, magnesium-sodium phosphates. Phosphates are the structural backbone of DNA and RNA. They are the P in ATP, the energy currency of all cells. Their presence on Bennu adds another critical piece of the puzzle. The fundamental ingredients for life are not unique to Earth. They are written into the fabric of the solar system's most primitive bodies. Ryugu and Bennu do not prove life was transported, but they prove, beyond any doubt, that its most complex and essential ingredients were. While meteorites connect Earth to its local neighborhood, panspermia also suggests a more audacious exchange between star systems. For this to happen, interstellar objects would have to act as couriers. For centuries, this was pure fantasy. But in 2017, the detection of Oumuamua, the first known interstellar visitor, changed everything. 2 years later, Comet Borisov confirmed it. These visitors proved that such objects are not just theoretical, they are real. Models now suggest trillions of these objects are adrift in the galaxy, and that many pass through our solar system. Do they carry organics? Almost certainly. Comet Borisov's spectrum showed carbon-based compounds. Could they carry dormant life? This is far more speculative. The timescales and radiation exposure are immense. But the X possibility cannot be entirely ruled out, especially if life were shielded deep within a large icy body. The greater meaning is one of principle. The galaxy is a more interconnected system than we knew. Materials can be exchanged between star systems. Even if life cannot make the leap, its chemical precursors certainly can. Of all the potential transfer scenarios, the most plausible is the exchange between Earth and Mars. The two planets are close neighbours, and their early histories were similar. Both were bombarded by asteroids for billions of years, a process that ejects debris from both. The evidence for this is tangible, resting in our museums, Martian meteorites, identifiable by their unique chemical and isotopic fingerprints. Tiny gas bubbles trapped inside some meteorites perfectly match the Martian atmosphere as measured by our own landers. This is definitive proof that rocks can travel from Mars to Earth. The reverse, ejecta from Earth landing on Mars, is also physically true. Simulations show millions of kilograms of Martian rock have landed on Earth. Some of these fragments arrive incredibly fast, in as little as 20 years. These rapid transits are crucial. For a microbe shielded in rock, surviving decades is plausible. Surviving millions of years is not. If ancient Mars ever hosted life, its microbes could have been delivered to Earth. Conversely, if Earth life arose first, it could have seeded Mars. This raises the profound possibility that if life exists on Mars, it may be our relative, sharing a common ancestor. Venus is often called Earth's toxic twin. It's the same size, but shrouded in a crushing atmosphere with surface temperatures hot enough to melt lead. And yet, high in the atmosphere, around 50 kilometers up, the cloud decks are surprisingly temperate. Temperatures and pressures are similar to Earth's. Some scientists have hypothesized that a microbial biosphere could exist there, floating on droplets of sulfuric acid. The controversial 2020 report of detecting phosphine gas, a potential biosignature, has since been strongly contested and largely refuted by subsequent studies. Still, the idea of an aerial biosphere keeps Venus on the list of intriguing locations, a potential, if unlikely, habitat. Far from the Sun, the icy moons of the outer planets hide vast, liquid water oceans. Saturn's moon, Enceladus, erupts with geysers, spraying plumes of its hidden ocean into space. The Cassini probe flew through these plumes and found salts, organics, and, in a stunning discovery, sodium phosphates, a critical ingredient for life's biochemistry. This confirms its subterranean ocean is not just water, but a chemically rich soup that could potentially support biology. Jupiter's moon, Europa, is another prime candidate. Its cracked, icy surface likely hides a massive ocean which may also vent plumes into space. For panspermia, these moons are relevant in two ways: as potential origins for life that could be ejected via plumes, and as potential destinations that could be seeded by material from elsewhere. They remind us that habitability is not just about rocky planets, and that these moons may be actively exchanging material with the rest of the solar system. Titan, Saturn's largest moon, is a truly alien world. It has a thick, nitrogen-rich atmosphere and a landscape of rivers and lakes, not of water, but of liquid methane and ethane. On its surface, water is frozen as hard as granite in a deep freeze of hundreds of degrees below zero. At first glance, it is utterly inhospitable. And yet, Titan is a factory for raw ingredients. Complex organic molecules are formed in its upper atmosphere by sunlight, raining down to create a smog and surface deposits of tholins. Titan is a prebiotic laboratory in a deep freeze, showing us alternative pathways to chemical complexity. For panspermia, Titan's importance is in demonstrating that the building blocks of complexity arise even in the most exotic and unexpected environments. 4 billion years ago, the solar system was a chaotic, violent place. Asteroids and comets impacted planets with a frequency we can hardly imagine. The collision that formed our moon was just one of many such cataclysms. This constant, heavy bombardment blasted debris from planets, scattering it across the inner solar system. In that era, Earth, Mars, and Venus were not isolated. They were part of an interconnected network, constantly exchanging material. Billions of tons of rock were transferred between them. If life, or even just complex prebiotic chemistry, emerged on one of these worlds, it would have had ample opportunity to spread to the others. This paints a picture of the early solar system as a microbial archipelago, a set of worlds linked by a common transport system. Life might not have needed to arise independently on each planet. A single origin event, perhaps on Mars or Earth, could have seeded its neighbors, creating a single family of biospheres. This reframes life's origin from a single planet event to a broader regional drama. For this to work, timing is critical. In the early solar system, the heavy bombardment provided the frequent transport mechanism. This coincided with the exact time that planets were cooling, oceans were forming, and atmospheres were stabilizing. These were windows of opportunity, periods when the environments were becoming habitable, just as the traffic of material between them was at its peak. If life began on Mars, which may have been habitable before Earth, its export to our world could have been rapid. Today, the solar system is comparatively quiet. Impacts are rare, and the window of frequent exchange is mostly closed. But billions of years ago, the timing may have been perfect. When considering panspermia, it is useful to ask, how many chances were there? Even if the odds of success for one rock are tiny, large numbers can make it probable. This is where a Fermi-style estimation is useful, breaking the problem down. Major impacts have happened countless times. Each can eject billions of kilograms of debris. Simulations show millions of fragments have been ejected from Mars alone. Models suggest roughly 1 in 100 of these may eventually intersect Earth's orbit. This still leaves tens of thousands of potential couriers from a single large impact. How many land softly? A tiny fraction, but a tiny fraction of a huge number can still be significant. Finally, consider time. Over billions of years, this process repeats. Panspermia doesn't need to be efficient, it only needs to succeed once. A single viable microbe arriving in a welcoming environment could have changed planetary history. The greatest filter between ejection and arrival is time. The duration of the transit dictates the plausibility. A journey of decades is survivable for dormant spores shielded in rock. A journey of millions of years due to cumulative radiation damage is almost certainly not. Computer models show a wide distribution. The average transit time is very long. But what matters are the outliers, the rare, fast transfers. A small percentage of rocks can make the crossing in under a century. Now, compare this to biology's resilience. DNA's half-life, even when frozen, is finite. Radiation and decay accumulate. But a window of decades or even a few centuries is well within the plausible survival limits for a hardy, dormant spore. Life just needs to be lucky once. Time is a powerful filter, but it is not an impassable absolute wall. Even with shielding, the void of space is hostile. 3 primary choke points exist for any traveler. First, ultraviolet radiation. This is a powerful sterilizer, shattering DNA. Without shielding, it is lethal in seconds. A thin layer of dust or rock is non-negotiable. Second, desiccation. The vacuum of space pulls all water from a cell, making it brittle. Spores are pre-adapted for this, having evolved to survive drought on Earth by packing their DNA in protective proteins. Finally, there is simple chemical decay. Over thousands of years, even without radiation, complex molecules will spontaneously break down. Biology has a finite shelf life. Success requires the alignment of all factors: a shielded microbe, a violent but not too hot ejection, and a rapid transit to a new, welcoming world. Arrival is not the final chapter. Most debris that reaches Earth burns up harmlessly in the atmosphere. Then there is the filter of the landing itself. A high-speed impact would sterilize the payload. But let us assume a fragment lands softly, perhaps in an early ocean, and carries viable spores. For panspermia to be meaningful, life must not only survive the journey, it must colonize the new world. It must find a compatible, habitable environment. In Earth's early oceans, such a place might have been common. This final stage, colonization, is the most speculative. A few cells might survive, but unless they can reproduce and outcompete any native, emerging chemistry, their journey ends there. Ultimately, the case for panspermia rests in the gap between simulation and experimentation. Models confirm that the exchange of rocks between Earth and Mars is not just possible, but common. Some of these journeys are fast enough for life to survive. Experiments confirm that biology is tough. Spores can survive the vacuum, radiation when shielded, and the shocks of launch and re-entry. What we have not yet tested is the entire chain of events at once. No experiment has yet tracked a real rock carrying real microbes on an actual interplanetary journey. Until that happens, panspermia remains a powerful hypothesis, stitched together from compelling but partial evidence. It is neither proven nor disproven. Life has a fundamental quirk: homochirality. Amino acids, the building blocks of proteins, exist in two mirror-image hands, left and right. In a laboratory, chemistry produces a 50-50 mix. But all life on Earth is exclusively left-handed, L-form. Why? This mystery has long puzzled scientists. If life arose from a random chemical soup, why this total preference? Meteorites like Murchison offer a clue. They contain a small but consistent excess of the L-form amino acids. The imbalance is tiny, but it's there. This suggests that forces in space, perhaps interactions with polarized light in interstellar clouds, can create a slight bias. If so, Earth may have received a pre-biased chemical kit. The primordial soups may not have been a 50-50 mix. Once life began, this small initial advantage could have been amplified by natural selection until it became the absolute rule. This doesn't solve the mystery, but it shows that this fundamental trait of life is not just an earthly phenomenon, it has cosmic roots. Another way to trace a molecule's origin is through isotopes, variants of an element with different weights. The ratio of these isotopes in a molecule functions as a chemical fingerprint, revealing where and how it formed. Carbon on Earth is mostly carbon-12. Meteorites often show different ratios of carbon-13, reflecting their formation in different, colder parts of the solar system. Hydrogen is also a key marker. The ratio of deuterium heavy hydrogen to normal hydrogen varies widely. We can compare the water in comets, asteroids, and Earth's oceans to see if they share a common source. These isotopic passports allow scientists to trace a molecule's journey through space and time. When we find unusual isotopic ratios in the organic molecules within a meteorite, we are seeing the signature of chemistry older than our planet. Isotopes are silent witnesses to this cosmic migration. Beyond amino acids, life needs sugars, nucleobases for RNA and DNA, and phosphates for energy and structure. For decades, these were assumed to be products of Earth's own biology, but recent discoveries have proven their extraterrestrial origin. The pristine Ryugu sample, returned by Japan's Hayabusa 2, contained uracil, an RNA base, and niacin, a B vitamin. This proved that fundamental components of our genetic and metabolic systems form naturally on asteroids. The Bennu sample, returned by NASA's OSIRIS-REx, contained another surprise: magnesium-sodium phosphates. Phosphates are the backbone of our genetics and the energy currency of our cells. Their presence on a primitive asteroid is a profound discovery. Even further out, the Cassini probe found that Enceladus's plumes spraying its hidden ocean into space contained sodium phosphates. This confirmed its hidden ocean is rich in this critical element, once thought to be rare. The takeaway is that life's ingredients are not rare, but widespread. The universe is rich in prebiotic chemistry, scattered across moons and asteroids, waiting for the right conditions. The constant challenge in studying meteorites is contamination. Earth is saturated with the very molecules scientists are looking for. It is incredibly difficult to distinguish a truly extraterrestrial signal from a terrestrial contaminant. Early, sensational claims of microfossils in meteorites, for example, were later found to be terrestrial contamination or simple misinterpretations of rock formations. To combat this, scientists use strict protocols. Samples are collected quickly from ice or deserts. Isotopic ratios are a key tool, as extraterrestrial molecules often have a fingerprint different from Earth's. But this is precisely why sample return missions are a game changer. The Ryugu and Bennu findings are so powerful because the samples were collected in space and sealed, bypassing Earth's contaminating biosphere entirely. They are pristine. If panspermia, or at least chemical seeding, were true, what would we expect to find? First, we would expect to find a full suite of prebiotic molecules in meteorites. This has been confirmed. Second, we would expect these molecules to have isotopic signatures proving their off-world origins. This is also observed. Third, we might expect to see hints of a bias that life later adopted, like the excess of L-form amino acids. This has also been found. Finally, we would expect life's appearance on Earth to be rapid, happening as soon as the planet was habitable, since the starter kit was delivered. This is also consistent with the geological record. These points do not prove panspermia, but they are all consistent with the hypothesis. They show Earth was not an isolated system. Conversely, what if life is entirely a product of Earth abiogenesis? In this scenario, all the organic molecules delivered by meteorites are just background noise, an irrelevant distraction. The critical, life-starting chemistry would have happened here in our own tidal pools or hydrothermal vents, independent of space. Homochirality, the left-hand preference, would need a purely terrestrial explanation, perhaps from reactions on mineral surfaces. This model keeps the story of life self-contained. It highlights the wonder of abiogenesis, that Earth's own chemistry was clever enough to cross the threshold into biology all by itself. In 1984, a team in Antarctica found a meteorite designated ALH8401. Years later, it was confirmed to be from Mars. In 1996, a NASA team announced they had found what looked like nanofossils inside, tiny worm-like shapes that they interpreted as possible remnants of Martian microbes. The news was explosive, even prompting a presidential announcement. But scientific skepticism quickly and rightly followed. Critics pointed out the structures were far smaller than any known life, and that similar shapes could be formed by non-biological geological processes. The consensus eventually shifted. The evidence was ambiguous and not sufficient to support the extraordinary claim. ALH84AC4A01 is now a classic cautionary tale. Morphology. What something looks like is seductive but notoriously unreliable. It proved that extraordinary claims require ironclad, unambiguous evidence. In 2001, a strange red rain fell over the state of Kerala, India. The colour was vivid, staining clothes, and led to wild speculation. A few researchers proposed an extraterrestrial source, suggesting the red particles were alien cells delivered by a comet fragment. However, subsequent, rigorous analysis found a mundane, though still interesting, explanation. The particles were identified as terrestrial spores from a local species of alga which had been swept up into the high atmosphere by monsoon winds and then rained down. The lesson was simple. Unusual does not mean extraterrestrial. Both of these episodes underscore a central truth. In the search for life, evidence must be treated with extreme care. Such claims demand multiple, independent, converging lines of evidence. Chemistry, isotopes, and morphology must all tell the same unambiguous story. The history of these false positives shows how easily enthusiasm can outrun data. This is why planetary protection, clean room assembly, and rigorous peer review are not bureaucratic hurdles. They are essential safeguards to ensure that when a discovery is announced, it is real. The most important lesson is humility. Real evidence of alien life will survive scrutiny. Until then, caution is our most important scientific tool. In 1973, Francis Crick and Leslie Orgel published their provocative paper on directed panspermia. They suggested life on Earth might have been deliberately seeded by an advanced civilization. They weren't suggesting ancient aliens, but rather that a distant intelligence might have, as a scientific project, launched robotic probes carrying hardy microbes toward promising young solar systems. Their paper was largely a thought experiment designed to challenge assumptions. Today, however, the idea is no longer purely hypothetical. We are on the verge of being able to do it ourselves. We have sent probes beyond our solar system and are learning to engineer life. This moves directed panspermia from science fiction to a pressing ethical question. The argument for directed panspermia centers on a perceived duty to life itself. Life, as far as we know, is fragile and confined to one planet. Asteroids, supervolcanoes, and eventually our own sun threaten its existence. Some argue we have a moral obligation to back up the biosphere, to spread the seeds of life to ensure it survives, even if Earth does not. The case against is equally powerful. First is the problem of contamination. If we seed a world like Europa, we could wipe out a native alien biology that was already there, destroying the very thing we seek to find. Second is the problem of hubris. We can barely manage our own planet's ecosystems. To assume we have the wisdom to engineer another's is the height of presumption. Third is the ethics of consent. This could be seen as a form of cosmic colonialism, imposing our biology on a world that cannot agree to it. The debate is one of values. Is the goal to propagate our kind of life, or to respect the autonomy of other worlds, even if they remain barren? This brings us to the Prime Directive, a concept from science fiction that has become a real-world policy problem. Do we interfere, or do we observe? International law, specifically the 1967 Outer Space Treaty, already forbids harmful contamination of celestial bodies. Planetary protection protocols are the practical application of this principle. We sterilize our Mars rovers precisely because we do not want to seed the planet. Furthermore, pristine worlds hold an intrinsic scientific value. To irreversibly alter an alien environment before we have even had a chance to study it would be a tragic loss. On the other hand, non-interference is also an active choice. To watch a habitable but sterile world remain barren for billions of years could also be seen as a failure. The question is not just can we seed life, but should we? And who decides? A core strength of science is that its ideas are testable. Panspermia and abiogenesis make different, testable predictions. Abiogenesis, the theory of an independent origin, predicts that life here should be unique. If we find life on Mars and it is chemically different, if if it uses right-handed amino acids or a different genetic code that would strongly support multiple independent origins. Panspermia predicts the opposite. It predicts continuity. If life has spread between worlds, Martian life should be our relative. It should use left-handed amino acids and DNA, and its genetic code should be familiar. Familiar life supports panspermia. Truly alien life supports abiogenesis. The universe holds the answer. To make this comparison, we would look for three key markers: the genetic code, molecular chirality, and phylogenetic trees. The genetic code, the dictionary that translates DNA into proteins, is universal on Earth. Finding the same code on Mars would be powerful evidence of common ancestry. Chirality, as we've discussed. If Martian life is right-handed, it would be definitive proof of an independent origin. And finally, if we could sequence its DNA, we could build an evolutionary tree to see if Martian life nests within Earth's tree, or if it branches off from a completely separate root. This would tell us once and for all if we are siblings or strangers. Another way to test the idea is to study the delivery vehicles themselves. Pristine samples from asteroids and comets are key. The Hayabusa 2 and OSIRIS-REx missions have already confirmed that the chemical building blocks are out there. Future missions will refine this. ESA's Rosetta probe already found amino acids in the gas of a comet. And as for interstellar visitors, while we've only seen Oumuamua and Borisov from afar, future observatories may be able to intercept such a traveler. If we ever find complex prebiotic chemistry, or improbably biology, on an interstellar rock, it would prove that the exchange of life's toolkit is a galactic process. This is why the planned Mars sample return mission is so crucial. It aims to bring back sealed tubes of rock and soil collected by the Perseverance rover for analysis in Earth's best labs. The first challenge is back contamination. The samples must be handled in facilities of unprecedented sterility to protect Earth. The second is recognizing an unambiguous biosignature. Shapes are not enough. Chemical proof is required. If these samples reveal life similar to ours, panspermia gains massive support. If they reveal life that is completely different, abiogenesis gains support. If they reveal nothing, the question remains. Either way, the results will be transformative. Beyond Mars, the icy moons offer an incredible opportunity. Enceladus is spraying its ocean into space. Future probes could fly through these plumes with instruments specifically tuned to detect complex biosignatures, looking for amino acid patterns or lipid-like molecules. Europa may also have plumes. This method allows us to sample an alien ocean without the risk and expense of drilling through kilometers of ice. Imagine the implications. A probe flies through a plume and detects biomolecules with the exact same left-handed bias as ours. That would be a powerful hint of a shared origin. Detecting the opposite bias would be just as profound, proving a second independent genesis. These ocean world plumes are one of our most exciting near-term chances to test this grand hypothesis. If panspermia is true, our identity changes. We are cosmic migrants. Our lineage would not begin in Earth's primordial soup, but in an ancient rock, a comet, or a distant, unknown world. Every cell in our body would carry the legacy of a journey across the void. Life would be a galactic family, and we would be one branch. And if it is not true, if life arose here independently, the story is no less profound. It would mean that Earth's chemistry on its own was clever enough to cross the threshold into biology. It would prove that the universe is capable of independent genesis, perhaps countless times, on any world where the conditions are right. In both cases, the implication is the same. Life is not a fluke, but a natural expression of the cosmos. No matter the answer, panspermia leaves us with a sense of wonder. The cosmos is chemically restless. Meteorites carry amino acids. Asteroids hold phosphates. Ocean moons vent organics. Everywhere we look, the building blocks of life are present. The universe appears biased toward complexity. We inhabit not a barren void, but a cosmos fertile with potential. We just don't know how many of those seeds have bloomed. And now, as you settle into rest, let's zoom out and see the story as one. Picture a single microscopic grain of dust floating in the dark between stars. It is insignificant, yet it carries the potential for something astonishing. On its surface, starlight coaxes simple molecules into amino acids. An icy mantle protects its fragile cargo. Over eons, it gathers with others, becoming part of a comet or an asteroid. These bodies drift through the solar system, and some, inevitably, strike young, new worlds. On the early Earth, one such delivery may have provided the critical ingredients that tipped the chemical balance toward life. Out of dust and rock, oceans filled with molecules that learn to copy themselves, to adapt and to grow. The unbroken chain of life that leads directly to your own consciousness began with violence and patience, with dormancy and chance. You are a part of this story. You are the material of stars that learned to think, oceans that learned to dream, and cells that learned to wonder. In your consciousness, the universe is observing itself. So let these questions settle as you rest. Are we children of this planet or children of the cosmos? Do our cousins wait on distant worlds, or are we one of many independent beginnings? The answers will come slowly as we continue to explore. For now, you can simply close your eyes, knowing that whether seeded from beyond or born of this earth, you are part of a universe that is endlessly fertile with possibility. I hope you sleep well and dream peacefully. Good night.